Okay, next thing we're going to talk about is volumes of revolution, and I'm going to break this up into two different videos. One, we're going to talk about the washer method. This is also referred to as discs sometimes. So we're going to look at that method separately from cylindrical shells. That'll be on the next video. All right, so what I've found here is a website. So if you want to pause the video and write down that website, you can go back to it and kind of look at some of these other images. But I just for now want to take a look at, I don't know, one of these. I don't know, let's take a look at, I want to do a function that's pretty easy. So let's do this one right in the middle here, where y equals 1, x equals 0, and y equals x squared. All right, so if I go to that one, now notice here's y equals, let's see if I can actually get this to work here. There's y equals x squared, there's y equals 1, here's x equals 0. What this is doing is it's now creating it partitioned that region into different slices, very small slices. And now it's taking a slice and it's revolving that slice about this x-axis. So it's taking this slice, it's revolving it about that x-axis and creating a washer. That's why this is called washers. See, there's a hole in the middle of it. That's what makes a washer. So there's the first slice and half a washer. There's a half a washer. There's another half a washer. Another half a washer with the next slice. Half a washer with the next slice. Half a washer with the next slice. So what we're going to do is integrate. We're going to be adding up all of those washers. Here it is filling in the full washers. Now when it does this, it's hard to tell. There's a hole in the middle of this that's kind of getting bigger and bigger as we move outwards. Now what this image is doing is taking that full thing and it's rotating it. And you'll start to see kind of a full solid come into view in just a second. We'll give this a minute to catch up. And you can see that what you're going to get is kind of a cylinder with this sort of cone taken out of the middle of it. All right, but the idea with all of this is that we are going to add up, we are adding, integrating washers. All right, so in this method, remember that the area of a disk is pi times the radius squared. So we're going to use this. And when we add these up, we are going to be integrating pi times the radius squared. Now, the trick on this, and there's a couple different things, so I'll tell you what I do first. First, I draw a picture. Sound familiar? I draw a picture so I can get an image of exactly what my radius looks like. So I draw a picture, and I'm going to draw a slice. So draw a slice of the region that we're going to be revolving. And I'm going to draw the slice, and then I'm going to draw a disc or washer, depending on if it has a hole in it or not. So this sort of gives me an image. Now, the next thing that I want to figure out is D what? What are we integrating with respect to? So what do we integrate with respect to? And then lastly, what is the radius? And what is the radius? And is there more than one? Is there more than one? Right, so these are all the questions that I kind of asked to put together this integral with the pi radius squared. Okay, let's do an example. Right, let's find the volume of the solid with a region bounded by, let's look at the function y equals root x. Let's do x equals 0, x equals 4, and y equals 0. This is going to bound our region. And for right now, let's revolve about the x-axis. And actually, for the sake of making this video a little bit shorter, on all of these, I'm just going to set up the integral. So let's see if I can actually get this up there. Set up the integral to find, oh, I already find, to find the volume of the solid with the region. Okay, so I'm just going to set these up. All right, so first thing I do is draw a picture. Draw the graph. We've got y equals root x. It looks like that. Y equals root x. X equals 0. That's going to be our y-axis there. And I'm sorry, y equals 0 is the x-axis. And then x equals 0 is the y-axis, and x equals 4. That would be right there. So there's 4. And then I've got this function y equals root x. So I'm going to take this whole region right there and revolve it about the x-axis. Okay, so the next thing I'm going to do is take a slice of this region. There's a slice of it. I'm going to take that and revolve that little slice about the x-axis, and it's going to give me a disc that looks about like that. Filled in disc there. All right, so that's my one representative disc from the middle of this region. So I take a slice and I revolve that about the x-axis. Okay, so now my next question was that, d what? What are we going to integrate with respect to? We are going to be adding up these discs, and these discs are all along the x-axis. So here's one, the next one would be over from it, next one over from that, next one over from that, and all of them are being added up over the x-axis. Right, so dx, everything in terms of x. So now my radius, I need the radius in terms of x. So this radius here, since it's from the x-axis and going upwards, that would be y, and y is equal to root x in this case. So my radius is going to be root x. All right, so when I do this integral, I would integrate pi, I usually stick that outside, pi times the radius, root x squared. And we're integrating over x. And all of these, I'm looking at my bounds right now, all of these discs are being added up from x equals 0 to x equals 4. Right, so there's my integral that would represent the area of this solid. And just to give you an idea of what this would look like, if we took this whole solid and revolved it about the x-axis, so if we took this and revolved it, there's the outer radius of it, and you would get this kind of solid, what is that? It's not quite a cone, so solid paraboloid. Okay, so that's what the 3D shape looks like, and in order to find the volume of that, we would take pi times the integral from 0 to 4. That comes from the x bounds. We're adding up the discs. Pi radius squared. The radius had to do with the function, and that function was root x. Okay, so I want to take this exact same shape, but now let's revolve it about the y-axis, so you can see how this would change. So same shape, or same region, but now let's revolve revolve about the y-axis. Okay, so I'm going to draw a picture, always. I had my root x, my x equals 4. So here's my region. I had y equals root x was my function. And now I want to revolve about the y-axis. All right, and remember the next thing that we would do is draw a radius in here. Now, if I'm revolving about the y-axis, if I start at the y-axis, I've got a radius from the y-axis all the way through to that x equals 4, and then I've got another one from there to the function. And if I drew a radius through the whole region and then revolved that about the y-axis, I get a washer. All right, so we're going to be adding up those washers. This is a washer now because it has a hole in it. If there's a hole, we usually have to think about two different functions, and we're usually going to have two, well, I can set it up in one integral, and I'm going to do that, but we have to think of it in two different pieces. Right, so we do have two different radiuses. The blue radius is the big radius, I'll do it with a capital R, and that radius is always constant at 4. So if I revolved that radius, notice I'd get like a Coke can, a full solid piece. Out from that solid piece, I want to subtract the hole in the washer. So I'm going to subtract where the radius, it's the green one, it's little r. This radius, because it goes from the positive y-axis over, has to do with this function, but that radius now is an x, and x would be equal to y squared. Now the other thing in here, I found my radiuses, and normally I would find the d what first. So this time our washers, here's one. If we drew another one, maybe we draw one a little bit below it, and then a little bit below that, and a little bit below that. And notice that all of these, when I'm drawing these, I'm drawing them along the y-axis. And so it's going to be dy. I need everything in terms of y. So here we go. Pi times the integral of the big radius squared. So I take the whole big thing, and then I'm going to subtract off the little radius, everything in terms of y, so it's the y squared, squared. And my y values, I'm looking at the bounds now, I've got to go back to the picture and look at my y values. Y starts at 0 and it ends right here, and that would be when x is equal to 4. And when x is equal to 4, y is equal to 2. So right up there, or at least right there, that would be the point 4, 2. So I'd integrate from 0 to 2. Those would be my y values. Okay, so this one's a little bit harder around the y-axis. Two different functions to think about. We have a big radius and a small radius. That's always going to happen if you have a washer versus a disc, a hole in it. So big radius squared minus small radius squared, and integrate it from 0 to 2. A common mistake right here is to take the big radius minus the small radius and then square all of that. And that gives you a completely different function. So that's a common mistake. Just be careful with that. You want to take the big radius squared, so you want to take pi r squared for the big one, and subtract off pi r squared for the little one. Okay, now the other thing that we can do with this, we're going to do a new example. Same region, but this time, let's rotate about, let's do x equals negative 2. All right. So here's the same picture. Y equals root x. X equals 4. This time, we are going to revolve about this line. X equals negative 2. We're going to be revolving about that one. Now it's the same idea. We want to take a slice of the region and then rotate that slice about the axis. Ooh, my circles are a little off on this one, but you'll get the idea. About the axis of rotation. So again, we get a washer. So washer, two different radiuses to think about. We have a big radius. Here's the outer radius. So big R, and then we'll have a small radius. And what are we going to integrate with respect to this time? So these discs are being added up over the x-axis. This is the x-axis right there. They're being added up over the x-axis, and so we want everything in terms of x. Okay, so my big radius, and again I'm going to do pi radius squared, so pi times the big radius has to do with this function. This function, this root x right there, that root x only goes from x equals 0 up. And so we have to add 2 onto that. Kind of draw that in there. This part of that radius is root x. It goes from the positive x-axis up. This other part, sorry. All right, well, sorry, I'm having some technical difficulties here. All right, so this lower part right here, I'll just kind of draw over that R. I couldn't erase it. So this lower part right there, because we're rotating about the line x equals 2, that lower part is 2. So the big radius there, the big radius is going to be root x plus 2, and we've got to square that big radius. And so there's the big one, minus the small one. Now the small one is the same throughout the entire thing. It doesn't have to do with the function anymore in this. The small radius is just always going to be 2, because that is the distance from the x-axis down to this line of rotation. It is always 2. So we would take that radius and square it. We're integrating with respect to x. Now for bounds, we look back to the picture, and I'm going to look at my x's, and x's go from 0 to 4. So we would integrate from 0 to 4. All right. And let's do one more of these examples. Okay, and actually now that I've done all of this might be a little confusing, but I don't want to go back and redo it. I just realized this is y equals negative 2. Let's change that. And let's change this to a y equals negative 2. Sorry about that. Hopefully that wasn't too confusing to begin with.